Imagine you're holding a coin. You flip it, and while it's spinning in the air, is it heads or tails? You might say, well, it's neither yet, it's just spinning. But here's the thing, once it lands, it's definitely one or the other. That's how our everyday world works. Things are either this or that, on or off, black or white, one or zero. But what if I told you that in the quantum world, that coin could actually be both heads and tails at the same time until you look at it, and that this bizarre property, this strangeness at the heart of reality, might be the key to building computers so powerful they could crack problems that would take today's best supercomputers longer than the age of the universe? This isn't science fiction. This is quantum computing, and it's one of the deepest mysteries Richard Feynman ever grappled with. So, me take you on a journey into the weird, wonderful world where the rules of reality bend, where particles can be in two places at once, where information can teleport, and where the future of computing isn't just faster, it's fundamentally different. And along the way, we'll uncover why Feynman, one of the greatest physicists who ever lived, became obsessed with this idea, and why he believed that nature itself was trying to tell us something profound. Let's start with something you already understand. Your computer, your phone, the device you're watching this on, they all work with bits. A bit is just a simple switch that can be either 0 or 1, off or on. Everything you see on your screen, every photo, every video, every word, it's all just millions and millions of these zeros and ones arranged in clever patterns. It's like building everything in the universe out of Lego blocks, but you only have two types of blocks to work with, a 0 block and a 1 block. And you know what? This system works incredibly well. We've built an entire digital civilization on it. But here's where things get interesting. Back in the early 1980s, Feynman was thinking about something strange. He was trying to simulate nature on computers, trying to model how atoms and molecules behave. And he kept running into the same frustrating problem. The quantum world, the world of the very small, doesn't follow the same rules as our everyday world. Atoms and electrons do things that seem impossible. They exist in multiple states at once. They influence each other instantly across vast distances. They behave like waves and particles simultaneously. And when Feynman tried to simulate this weirdness on a regular computer, the calculations became impossibly complex. To simulate just 40 particles behaving quantum mechanically, you did need more computer memory than there are atoms in the universe. Think about that for a second. The universe itself doesn't have enough stuff to let us calculate what 40 tiny particles are doing. That's when Feynman had his brilliant insight. He said, look, if nature is quantum mechanical, and we're trying to simulate quantum mechanics on a classical computer, we're basically trying to force the round peg of quantum reality into the square hole of classical computing. What if instead we built a computer that actually uses quantum mechanics? What if we let nature do the computing for us in its own language? This was a revolutionary idea. It was like someone trying to translate Chinese by first converting every character to English letters, then doing all the work in English, then converting back. Feynman was saying, why not just work in Chinese if the original text is in Chinese? Now, to understand why this is so powerful, we need to understand what makes quantum mechanics so weird. And the weirdness starts with something called superposition. Remember a coin flip? In the classical world, the coin is either heads or tails once it lands. But in the quantum world, before you measure it, a quantum coin can be both heads and tails at the same time. It's not that we don't know which one it is, it's that it genuinely is both simultaneously. I know this sounds crazy. Feynman himself said that nobody understands quantum mechanics, and he was right. But here's the thing. We don't need to understand why it works this way. We just need to accept that this is how nature behaves at the smallest scales, and we've proven it experimentally thousands of times. So what's a quantum bit, or a qubit? It's like a regular bit, but instead of being just 0 or 1, it can be 0, 1, or both at the same time in what we call a superposition. Imagine you have a spinning coin that's simultaneously showing both faces. Now, if you have one regular bit, it stores one piece of information, either a 0 or a 1. But one qubit, because it can be both, stores more information in a sense. It exists in multiple states simultaneously. But here's where the real magic happens. If you have two regular bits, you can store one of four possible values, 0001, 1011. But at any moment, your two bits are in just one of those states. However, if you have two qubits, they can be in all four of those states at the same time. With 3 qubits, you can represent all 8 possible combinations simultaneously. With 4 qubits, 16 combinations. Do you see the pattern? The number of states doubles with every qubit you add. This is exponential growth, and it's absolutely staggering. With just 300 qubits in superposition, you could represent more states simultaneously than there are atoms in the observable universe. Let that sink in. A device smaller than your hand using just 300 qubits could in principle explore more possibilities at once than there are atoms in all the galaxies, stars, and planets we can see. This is why quantum computers aren't just faster computers. They're a fundamentally different way of processing information. It's like the difference between searching for a specific book by checking every single shelf one by one versus somehow being able to look at every shelf in the entire library simultaneously. But there's a catch, and it's a big one. Actually, there are several catches, and they're what make quantum computing so difficult. The first catch is something called decoherence. Remember how I said a qubit can be both 0 and 1 at the same time? Well, this only works if the qubit is perfectly isolated from the outside world. The moment anything from the environment interacts with it, a stray photon of light, a vibration, a tiny fluctuation in temperature, the superposition collapses. The qubit is forced to choose to become either 0 or 1. And when this happens, you lose all that quantum magic. It's like trying to balance a pencil on its point. Theoretically possible, but the slightest breeze, the tiniest vibration, and it falls. Except qubits are millions of times more sensitive than any balanced pencil. They can lose their quantum properties in microseconds, sometimes nanoseconds. This is why quantum computers need to be kept at temperatures colder than outer space, just a fraction of a degree above absolute zero. They need to be shielded from magnetic fields, vibrations, and radiation. They're some of the most delicate, finicky devices humans have ever built. The second catch is measurement. Here's the paradox of quantum computing. While your qubits are in superposition, they can explore all possible solutions to a problem simultaneously. But the moment you try to read the answer, the moment you measure the qubits, the superposition collapses, and you get just one specific result. It's like having access to all possible answers, but only being able to retrieve one. So how is this useful? This is where quantum algorithms come in, and this is where true genius is required. Quantum algorithms are designed in such a way that the wrong answers cancel each other out through quantum interference, while the right answer gets amplified. It's like having 1,000 tuning forks all vibrating at different frequencies, but they're arranged so that most of them cancel each other out, and only the one true note rings clear. Feynman understood this problem deeply. He knew that building a quantum computer wasn't just an engineering challenge, it was a fundamental rethinking of what computation means. And he was one of the first to ask the right questions. What kinds of problems could a quantum computer solve that classical computers couldn't? How do you program something that exists in multiple states at once? How do you extract useful information from a system that collapses the moment you look at it? Now let's talk about what quantum computers might actually be able to do. There's one application that really captured people's imagination, and it's both exciting and a little scary. It's about breaking codes. You know how your credit card information is kept safe online, how your messages can be encrypted. Most of modern encryption relies on a simple mathematical fact. It's really easy to multiply two large prime numbers together, but it's incredibly hard to take a huge number and figure out which two primes were multiplied to create it. With today's computers, if you use big enough primes, the factoring problem would take thousands or millions of years to solve. But in 1994, a mathematician named Peter Shor created a quantum algorithm that could factor large numbers exponentially faster than any known classical algorithm. A quantum computer with enough qubits could break most of the encryption that protects the internet in hours or even minutes. This got a lot of attention, particularly from intelligence agencies and cybersecurity experts. The entire infrastructure of secure communication could become vulnerable. Now, before you panic, we're not there yet. Building a quantum computer with enough stable qubits to break real-world encryption is still a huge challenge. But it's no longer theoretical. It's a matter of when, not if. And that's why governments and companies are already working on quantum-resistant encryption, preparing for a future where quantum computers are real. But code breaking is just the flashy headline. The real power of quantum computing might lie in something Feynman originally cared most about, simulating nature itself. Remember, this was his original motivation. Nature is quantum mechanical, so quantum computers should be able to simulate quantum systems naturally. Think about chemistry. Every chemical reaction, every molecule, every drug, every material, they all behave according to quantum mechanics. The electrons in atoms and molecules exist in superpositions. They re-entangle with each other. They do all the weird quantum things. When chemists try to design new molecules or predict how a protein will fold, they're essentially trying to solve quantum equations. And with classical computers, we can only approximate the solutions for relatively small molecules, but a quantum computer could simulate the actual quantum behavior of molecules directly. This could revolutionize drug discovery. Instead of testing millions of compounds in labs, we could simulate them accurately on quantum computers first. We could design new materials with properties we specify, materials that are stronger, lighter, more conductive, more efficient. We could understand complex biological processes at a molecular level. Feynman would have loved this. He was always fascinated by the machinery of nature, how things actually work at the deepest level. And quantum computers offer a window into that machinery that we've never had before. There are other applications too. Optimization problems, where you need to find the best solution among countless possibilities. Think about routing delivery trucks through a city, scheduling flights at an airport, managing power grids, designing financial portfolios. These problems get exponentially harder as they get bigger, but quantum algorithms might be able to find solutions much more efficiently. Machine learning and artificial intelligence could be transformed. The pattern recognition and optimization at the heart of AI might be done far more efficiently on quantum computers. We don't fully understand how yet, but the potential is enormous. Climate modeling, understanding turbulence in fluids, simulating nuclear reactions. All of these involve complex systems with many interacting parts, exactly the kind of thing quantum computers might excel at. But here's what I find most beautiful about this whole story. Quantum computing isn't just about building a faster calculator. It's about learning to think in a completely different way. Classical computers forced us to think in terms of logic gates and sequential operations, ones and zeros marching in orderly rows. Quantum computers are teaching us to think in terms of probabilities and interference, of states that exist in limbo, of information that's fundamentally different from classical information. There's a concept in quantum mechanics called entanglement, and it's perhaps the strangest thing, of all. When two qubits become entangled, they become connected in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein hated this idea. He called it spooky action at a distance and thought it meant quantum mechanics must be incomplete. But experiments have proven that entanglement is real. Measure one entangled particle, and its partner, even if it's on the other side of the galaxy, instantly knows. In quantum computing, entanglement is a resource. It's what allows qubits to work together in ways that classical bits never could. Multiple qubits can become entangled, creating states that cannot be described by looking at each qubit individually. They become a unified quantum system, and this is where the real computational power comes from. Feynman would do these thought experiments where he'd imagine shrinking down to the atomic scale and watching quantum mechanics in action. He'd think about electrons as little arrows spinning in all directions at once, about waves of probability spreading through space, He made the abstract concrete by visualizing it, even when the visualization was just a mental tool and not literally what was happening. And that's what we need to do with quantum computing. We need to develop intuitions, mental models, ways of thinking about these systems, even though they're fundamentally unlike anything in our everyday experience. Here's something that really drives this home. There's a thought experiment called the double slit experiment. You shoot particles, let's say electrons, at a barrier with two slits. Behind the barrier, you have a detector screen. Now, if electrons were like tiny bullets, they'd go through one slit or the other and hit the screen in two bands. But that's not what happens. Instead, you get an interference pattern, bands of light and dark, just like when waves overlap and neither reinforce or cancel each other out. The truly bizarre part, this happens even if you shoot the electrons one at a time. Each electron somehow goes through both slits simultaneously, interferes with itself, and creates the pattern. It's as if each individual electron is exploring all possible paths and interfering with its own possibilities. But here's the kicker. If you try to observe which slit the electron goes through, if you put a detector at the slits to watch, the interference pattern disappears. The electron behaves like a particle again, going through one slit or the other. The very act of measurement changes the outcome. The electron seems to know it's being watched. This isn't about consciousness or magic. It's about the fundamental nature of quantum information. When you make a measurement, you're interacting with the system, entangling your measurement device with the quantum state, and this interaction forces the system to give up its quantum superposition. This is the tightrope that quantum computers walk. You need superposition and entanglement to do the computation, but you need measurement to get an answer. And the whole thing is so fragile that the slightest environmental noise can destroy it. It's like trying to do calculus on a soap bubble before it pops. So where are we now with actually building these things? Well, there are several different approaches, and it's not yet clear which will win. Some quantum computers use superconducting circuits, loops of wire cooled to nearly absolute zero, where electricity flows without resistance and quantum effects become visible at a scale we can engineer. Companies like IBM and Google are pursuing this approach. Others use trapped ions, individual atoms held in place by electric fields and manipulated with lasers. The qubits are literally individual atoms, and the quantum states are different energy levels of the electrons in those atoms. This approach tends to have better coherence times, meaning the qubits stay quantum for longer, but it's harder to scale up. There are photonic quantum computers that use particles of light, topological quantum computers that use exotic states of matter, and quantum annealers that are specialized for certain types of optimization problems. In 2019, Google announced they'd achieved quantum supremacy, a controversial term meaning they'd performed a calculation on a quantum computer that would be impractical on a classical computer. The task was admittedly a bit contrived, designed to play to the quantum computer's strengths, but it was a milestone. It showed that quantum computers could do something, even if it wasn't yet useful, faster than classical computers. But we're still in the very early days. The quantum computers we have now are what we call NISQ devices, noisy intermediate scale quantum. They have tens to hundreds of qubits, but those qubits are noisy, prone to errors. They can run quantum algorithms for only brief moments before decoherence ruins everything. To run really useful quantum algorithms, to break encryption or simulate complex molecules or solve real optimization problems, we'll need quantum error correction. This is the idea that you can use multiple physical qubits to encode one logical qubit in such a way that you can detect and correct errors without destroying the quantum information. But error correction is expensive. It might take hundreds or thousands of physical qubits to make one reliable logical qubit. So we're in a race. Can we build quantum computers with enough qubits, low enough error rates, and good enough connectivity between qubits to implement error correction and run useful algorithms? Or will we hit a fundamental wall, some limit of nature that makes practical quantum computing impossible? Feynman would have loved this uncertainty. He thrived on problems where the answer wasn't known, where you had to think deeply about what nature was telling you. He'd probably be in the labs, trying things, making mistakes, learning from failures. He famously said that science is a lot more like looking for a black cat in a dark room where there might not even be a cat than most people realize. But here's what I think is most profound about quantum computing. It's teaching us that information itself is physical. This might sound obvious, but it's a deep insight. Information isn't some abstract thing floating around. It's always encoded in something physical, whether that's ink on paper, magnetic domains on a hard drive, or the quantum state of an atom. And the physical properties of that encoding matter, classical information, bits, can be copied, deleted, read without disturbing them. But quantum information is different. There's a no-cloning theorem that says you can't make a perfect copy of an unknown quantum state. There's the measurement problem. You can't read quantum information without changing it. Quantum information can be entangled, distributed across multiple particles in ways that classical information cannot. This means that the universe is, in some deep sense, quantum computational. The way particles interact, the way information propagates through space and time, it all follows quantum rules. We live inside a quantum computer, and classical reality is what emerges when we look at it, when we become entangled with it through measurement. Feynman understood this. He saw that physics wasn't just about particles and forces. It was about information, about how nature processes and stores and transforms information. Quantum mechanics isn't just a mathematical formalism. It's telling us something profound about the nature of reality itself. There's a principle that Feynman often invoked called the principle of least action. It says that nature always takes the path that minimizes a certain quantity called action. But in quantum mechanics, this gets weird. A particle doesn't take one path. It takes all possible paths simultaneously, and each path contributes to the final amplitude, the probability of where the particle ends up. The paths interfere with each other, and the interference pattern is what determines reality. This is what quantum computers exploit. They set up a superposition of all possible computational paths. Let those paths interfere with each other according to quantum rules, and design the interference so that wrong answers cancel out and the right answer is amplified. It's nature's way of computing, and we're just learning to harness it. Now, I want to address something you might be wondering. If quantum computers are so powerful, will they replace classical computers? The answer is no, not entirely. Quantum computers aren't better at everything. They're better at specific types of problems that involve searching through vast spaces of possibilities, problems that involve quantum simulation, certain optimization tasks, cryptography, for everyday tasks, checking email, browsing the web, watching videos, editing documents. Classical computers will remain dominant for the foreseeable future. They're simpler, cheaper, more reliable, and perfectly adequate for these tasks. Quantum computers are specialists, not generalists. It's like asking if supercomputers will replace your laptop. No, because you don't need a supercomputer for most things. But when you need to model climate change or simulate a nuclear explosion, a supercomputer is invaluable. Quantum computers will be similar. They'll be tools we use for specific problems where their unique abilities make a difference. But in the long run, who knows? Maybe decades from now, we'll have cracked the problems of error correction and scaling, and quantum computers will become more commonplace. Maybe we'll find ways to integrate quantum and classical computing seamlessly. Maybe future smartphones will have quantum coprocessors for certain tasks, or maybe quantum computing will remain a specialized tool for researchers and industries dealing with quantum problems. What I find most exciting is what we don't know yet, the applications we haven't imagined, the discoveries waiting to be made. When the transistor was invented, nobody predicted smartphones or the internet. When quantum mechanics was being eloped in the 1920s and 30s, nobody imagined lasers or MRI machines or GPS satellites, all of which rely on quantum effects. Quantum computing is still so new, so full of unknown unknowns, that the most important applications might be things we can't even conceive of yet. And that's thrilling. We're at the very beginning of understanding what's possible. Feynman gave a famous lecture in 1959 called "There's Plenty of Room at the Bottom," where he talked about the possibilities of nanotechnology, of building machines at the atomic scale. He asked, why can't we write the entire Encyclopedia Britannica on the head of a pin? Why can't we build tiny machines? At the time, people thought he was crazy. Now we do these things routinely. He was thinking beyond the limits of the technology of his day, asking what was possible in principle according to the laws of physics. And that's the right way to think about quantum computing. What's possible in principle? What do the laws of quantum mechanics allow? And then, how do we engineer our way there? A beautiful quote from Feynman where he says, "What I cannot create, I do not understand." He believed that the deepest understanding came from being able to build something to make it work. Quantum computing is the ultimate test of our understanding of quantum mechanics. Can we build a quantum computer? Can we make it do useful things? If we can, we truly understand quantum mechanics in a way that goes beyond just solving equations. And there's a flip side to this. By building quantum computers, we're also learning more about quantum mechanics itself. We're discovering new quantum phenomena, new WIs, that quantum systems behave when engineered in certain ways. Quantum computing is both applied physics and fundamental research at the same time. Let me leave you with this thought. The universe is quantum mechanical. That's not a theory or a guess, it's an observed fact. Everything, at a fundamental level, follows quantum rules. The world of classical physics, the world of our everyday experience where things are either here or there, where effects have local causes, where information is simple and copyable, this world is an approximation, a special case that emerges when quantum systems get big and interact with their environment. We spent 300 years building a technological civilization based on classical physics. Steam engines, electricity, radio, computers, all of it built on the classical approximation. And it's been incredibly successful. But now we're learning to work with the full quantum reality underneath. We're learning to harness superposition, entanglement, and interference. We're building machines that don't just use quantum effects accidentally, but that are fundamentally quantum in their operation. This is a new chapter in human technology, and we're writing the first pages right now. Quantum computing might transform cryptography, chemistry, materials science, and artificial intelligence. Or it might turn out to be more limited than we hope. We don't know yet. But what we do know is that this journey, this attempt to build computers that work the way nature works at its deepest level, is teaching us profound things about reality itself. It's showing us that the universe is far stranger, far more subtle, far more beautiful than our everyday. Why intuition suggests Feynman spent his life exploring this strangeness. He taught us that nature has her own language, and if we want to understand her, we need to learn that language, not force her into our preconceptions. Quantum computing is us learning to speak quantum, to think in qubits and superpositions, to program with interference and entanglement. And here's the deepest mystery of all. Quantum mechanics works. We can predict the behavior of atoms and electrons and photons with incredible precision. We've tested it in countless experiments. But we still don't really know why the universe is quantum. Why does nature work this way and not some other way? Why superposition? Why measurement collapse? Why entanglement? These questions don't have answers yet. Maybe they never will. But by building quantum computers, by pushing the boundaries of what's possible with quantum systems, we're at least asking the questions in a new way. We're not just observing nature's quantum behavior, we're participating in it, manipulating it, using it. You started this journey thinking about a flipped coin, something simple and classical. Now you understand that at the deepest level, reality isn't like that coin at all. It's a shimmering superposition of possibilities, constantly interfering with itself, collapsing into definite outcomes when observed, yet fundamentally indeterminate until that moment. Quantum computing isn't just the next revolution in technology. It's a new way of thinking about what computation means, what information is, and how the universe processes reality itself. And whether quantum computers end up changing the world in practical ways or remain fascinating but niche tools, the journey of building them has already changed how we understand the deepest mystery of all, the quantum nature of existence itself. That's what Feynman knew, And that's what makes the story so compelling. We're not just building machines, we're unraveling the fabric of reality, one qubit at a time.